Okay, 10.3 is hypothesis tests for a population mean. To test hypotheses regarding the population mean, assuming the population standard deviation is unknown, we use the t-distribution rather than the z-distribution, just like when we were finding a point estimate for the population mean. So when we replace sigma with s, right, this follows the student's t-distribution with n minus 1 degrees of freedom. Okay, testing hypotheses about a mean follows the same logic and really same steps as testing a hypothesis about a population parameter. The only difference is we use the student's t-distribution rather than the normal distribution, so we got to remember that. And so here's again just a review of the properties of the t-distribution. It's different for different degrees of freedom. It's centered at 0 and symmetric about 0. The area under the curve is 1. Okay, because of the symmetry, the area under the curve to the right of 0 equals the area under the curve to the left of 0, which equals a half. As t increases or decreases, the graph approaches but never equals 0. The area in the tails of the t-distribution is a little greater than the area in the tails of the normal distribution because using s as an estimate for sigma introduces more variability. Remember, I think we looked at, a superimposed t-distribution on a standard normal, and we could see the difference in it a little bit. But as the sample size increases, the density curve of t gets closer and closer to the standard normal density curve. So this result occurs because as the sample size increases, remember our law of large numbers. Okay, so testing hypotheses regarding a population mean. So provided that the sample is obtained using simple random sample and it has no outliers. Now remember, this is different from population proportion, but the same as a population mean from the previous chapter. We look for those outliers, okay? And the sample size is greater than 30, then we can assume it's normal, okay? And the sampled values are independent of each other. So considering those things, we still have step 1. We determine the null and alternative hypotheses. Same exact thing, except we've got a mu here, right? Instead of a p, a two-tailed test, a left-tailed test, a right-tailed test. Step 2, select or be given a level of significance depending on the seriousness of making a type 1 error. Okay, and then just like in the population proportion, we've got our classical approach and we've got the p-value approach. Okay, so for either one, really, we're going to compute the test statistic, and here's the formula that we're going to get our test statistic, but it's going to follow the t-distribution. Okay, and then we'll use the table to determine the critical value. Okay, critical regions in the two-tailed test, the left-tailed test, the right-tailed test. We're going to compare the critical value with the test statistic to decide when we need to reject the null hypotheses and then state our conclusion. Okay. On the p-value approach, we're going to compute the same test statistic. Okay. But then we're going to actually find the area in this critical value, or in other words, the probability of being in that area, right? Same thing, two-tailed, left-tailed, right-tailed. And then if the p-value is less than alpha, reject the null hypothesis, state the conclusion. Or we can use technology to find the p-value. Okay, so notice that this procedure that we just talked about requires either that the population from which the sample was drawn be normal, and then we're good if we know it's normal, or that the sample size be greater than or equal to 30. Okay, minor departures from normality will not adversely affect the results of the test, but if the data has outliers, this procedure should not be used. So we're going to verify these assumptions by constructing box plots to discover if there are outliers. If the box plot reveals outliers, we move to non-parametric methods, which is not in this course, okay? But remember that. We got to make sure there are no outliers or n is greater than or equal to 30. Okay, so let's look at an example. So assume the resting metabolic rate, or MR, of healthy males is in complete silence is 5,710 kilojoules per day. Researchers measured the RMR of 45 healthy males who were listening to calm classical music and found their RMR, resting metabolic rate, to be 5,708.07 with a standard deviation of 992.05. At the 5% level of significance, is there evidence to conclude that the mean RMR of males listening to calm classical music is different than this 5,710 kilojoules per day? Okay, so we're going to assume that the RMR of healthy males is 5,710 kilojoules per day. So notice this is a two-tailed test, right? It just says is different. Because the sample size is large, right, larger than 30, in other words, we can say the distribution is approximately normal and just proceed to our steps. So step one, let me get a pen here. So step one is state our hypotheses. So our null hypotheses is that the mean is 5,710. And our alternate hypothesis is that it is not 5,710. Okay, step two is determine your level of significance, and they have given us that. Okay, so then step three, we compute that test statistic. Okay, so our test statistic. Okay, remember we have a formula for that, so I'm plugging into this formula. Just plugging our information in there. So X bar, 5708.07 minus the mean that we're assuming is the mean over the standard deviation over the square root of n. All right, so let's see what we get when we enter that in our calculator. Okay, I got negative 0.013. Okay, so because this is a two-tailed test, we need to determine the critical value at the alpha equals 5 level of significance with 45 minus 1, so 44 degrees of freedom, right? Now, also, because it's a two-tailed test, right? This is what I'm looking for. So I'll go across on my chart, okay? Let's see, at 44 degrees of freedom. Now remember, 44 is not on here. It jumps from 40 to 50, so we're going to use 40. We're going to go to the nearest one. So 40, and I'm going to go over until I find the column 0.025, and I see that piece of 0.025 is 2.021. So what that means is I have negative 2.021 here, positive 2.021 here, and this is our critical area. Anything in there. Okay, so I go back and I look at my test statistic, which is negative 0.013. So it's about, so here's 0. So it's about right here. Well, it's not even that far, but you get the idea. It's right here. It's not in the critical region. Not in the critical region. So we fail to reject the null hypotheses. We don't accept it. We just fail to reject the null hypotheses. That's the classical approach. Okay. Now, if I were doing the p-value approach, this is all the same. Every bit of this to right here is the same. Okay? The only difference is, instead of looking for these values, I'm looking for the probability of being in this region. Okay, so now on the next slide, I've put a copy of our T-chart so we can see what we're doing. So kind of keep this in mind, and you should have this written down. I've got to erase it to move to the next slide. But here's what we're looking for, and here's the difference between the two approaches. All right, so I'm still looking, let me get my pen back. So I'm still looking over here at 40 degrees of freedom, but this time instead of going across and looking here and seeing what my value is, I am looking for that negative 0.013 in here, right? Oh, and look, this goes 0.6, 0.8, 1 point. It just keeps getting larger and larger and larger. So my negative 0.013, my test statistic that I found, is here, right? It's over here somewhere. Meaning that 0.25, right? So this is 0.25 needs to be doubled because it's a two-tailed test, right? So it means this and this added in here is 2 times 0.25 or 0.5. And because 0.5 is less than our level of significance, because 0.5 is much greater than our level of significance, once again, that tells us that we fail to reject the null hypotheses, right? It's not unusual, right? It's 50%, around 50% chance of it happening. Not unusual at all. So we fail to reject. But notice the difference when I'm doing the classical approach. Okay, when I'm doing the classical approach, I look across here at my alpha. My degrees of freedom is 40, and alpha was 0.025. Okay, and I get my T sub alpha score. I get the score that goes right here. Right? If I'm doing the p-value approach, I'm looking for that test statistic in here. Does that make sense, the difference? Okay, so I'm looking for 0.0, what was it? 013. Okay, hopefully that made sense. We'll do another one. Okay, so according to the United States Mint, quarters weigh 5.67 grams. A researcher is interested in determining whether the state quarters have a weight that's different from 5.67 grams. He randomly selects 18 state quarters, weighs them, and obtains the following data. Okay, so here's our list of data. And it says at the 5% level of significance, is there evidence to conclude that state quarters have a weight different than that 5.67 grams? Okay, notice I only have 18. Oh, it says right there, 18 data values. So I have to, before I can just proceed, I've got to make sure there's not any outliers. So I could draw a box plot by hand, or I could let my calculator draw that. And I'm going to do that because I want this data in my calculator anyhow, right, for various things we might do on it. So I'm going to, first of all, I'm going to enter that data in my calculator. Okay, so you go into Stat, and then Edit. Okay, go up to L1 if you have any items in that list and clear it, and then go down and enter each one of these. 5.7, 7. So I'm just entering these in my calculator. List. And if I look on that last one, it tells me that's my 18th value. So that helps me realize that, hey, that should be, I should have entered all of my values. Now, go up to your graphing keys, do the second y equals to hit that stat plot. Okay, turn your plot on if it's not already for that box plot. Okay, choose your box plot that shows the outliers and what you need there, and then go over to your format. So hit that zoom, and zoom stat is number 9. Okay, and it draws us a nice little box plot, and we can see that there aren't any outliers. Plus, if you need any of that data, don't forget you can go up to trace, and there's your minimum value, right? First quartile, median, etc., etc. But since there's no outliers, we can proceed with our steps. All right. So our null hypothesis is that mu is 5.67. Our alternative hypotheses, now notice it just says have something different. So not equal, oh, I need my mean. I've got data. Hey, good thing I've got that already, all that in my list, because now we can just go into, let's see, our calculator. Stat again, calc, one variable statistics. And it tells me that X bar is 5.702222. 5.702. Let's leave that for right now. Okay. So now we've got to compute our test statistic again. So we have that formula. So X bar minus the mean over, whoops, I need S so I can look back on my calculator, 0.04965. Because I'm using calculations, I'm in the middle of a calculation, I'm not leaving my final answer. That's why I'm doing an extra decimal or two, remember? In your calculations, leave an extra decimal or two. So 0.0497 over the square root of 18. All right, let's see what this is. Okay, I got 4.702, 5.67. Got 2.7316. Okay. It's a two-tailed test again. So what I'm looking for on my t-distribution, let's see, 17, right? It's 18 minus 1 degrees of freedom, so 17. And again, because it's two-tailed, I'm going across at 17 to see where it meets up with 0.025, and I get 2.11. Remember, the number gives us the one that goes to the right, but because it's symmetric, I know this one is negative 2.11. Okay, so 2.73 is way over here somewhere, right? Way over here. Oh, it's in the critical region. So this time we are going to reject the null hypothesis, right? So there is sufficient evidence, we would say, to conclude the mean weight of the state quarters is different than 5.67, right? We're going to reject that null hypothesis. Now, I'm going to go back and look one more time at how to do the p-value. So while I'm here, I'm going to erase this. Okay, so remember what we have. We still have our, this part's all the same. Everything's all the same. The difference is I'm looking for the area under here this time, the probability that you're in this area. Okay, so when I go back and look at my p-value, go back up to the chart. This time I'm looking, this time I'm looking at 17 degrees of freedom, and I'm looking for 2.73 across here inside my chart. 2.73. Okay, here we go. It's in between here. 2.73 is in between here. Because it's two-tailed, right? This is giving me this region. But my test is two-tailed, so I'm going to double this. So 0.02, if I double this one, and 0.01. Okay, that means that, right, there's the probability of it being in this region. And I wanted my level of significance to be 5%, 0.05. Okay, it's smaller than my level of significance. So once again, I still get the same conclusion. I'm going to reject that null hypothesis, right? This shows sufficient evidence to conclude that the weight of state quarters is different. Okay, so kind of the difference between those two approaches. When a large sample size is used in a hypothesis test, the results could be statistically significant, even though the difference between the sample statistic and the mean stated in the null hypothesis may have no practical significance. Practical significance refers to the idea that while small differences between the statistic and the parameter stated in the null hypothesis are statistically significant, the difference may not be large enough to cause concern or be considered important. So let's look at what that means with an example. Okay, in 2003, the average age of a mother at the time of her first childbirth was 25.2. To determine if the average age has increased, a random sample of 1,200 mothers is taken and is found to have a sample mean of 25.5 with a standard deviation of 4.8. Determine whether the mean age has increased using a significance level of alpha equals 0.05. All right, since our sample is 1,200, that's way more than 30. So we can use the approach we're talking about in this book. So first step is to get your pen. Okay, so to state our two hypotheses, mu equals 25.2. Or, now, this time it's one-tailed, whether the mean age has increased, or is it really that it's more than 25.2? Okay, we are given our level of significance again. Okay, so computing our test statistic, we've got x bar, which is 25.5, minus the mean, 25.2, that we're assuming is the true mean, 4.8 over the square root of 1,200. All right, so let's enter that, see what we get. Okay, 2.17. 2.17. Okay, because this is a right-tailed test, okay, then I don't have to double anything, and I'm just looking for 0.05. But since there's 1,200 minus 1, 1199, I need to look at that very last row, right? That very last row. If it's more than 1,000, we use the very last row. So I'm going across there to try to find 0.05, and I find, here's what we have, let's draw it, 1.645. Okay, I don't have to double it this time. 2.17 is over here. Okay, so because this test statistic is more than the critical value, we're going to reject the null hypotheses. Okay, now, so we just saw this is statistically significant to reject that null hypothesis and say the average age of a mother that the first time her given childbirth is more than 25.2, but we found that it's really 25.5. Is that practically significant? Not really. Okay, does it really matter if you're 25.2 years of age or 25.5 years of age at the time of your first childbirth? No, they're both just 25. You were 25. So even though it does show statistical significance, it is not practical significance. All right, the p-value test, now we could do by hand like we've shown on the last couple of examples, or we could let our calculator do it, right? So this time, let's let our calculator do it. All right, so we're going to go into statistics, over to test. Number 2 is t-test. Okay, so if we had the data like from before, we would click data and tell it to use list 1. But we've got the stats that we need. We've got all the stats we need. So we're going to go over and highlight stats. Okay. So then we're going to enter the mean is 25.2. Okay. X bar 25.5. Standard deviation 4.8. 1200. And this is a right-tailed test. And you can either draw it or tell it to calculate. And notice up there, it will tell you that your p-value is, I don't know why I put a period there. Your p-value is 0.015. Yes, if your p-value is less than your level of significance, once again, you reject that null hypothesis. Okay, so you could also do that on the calculator for the p-value one. Okay. The reason that the results from that example were statistically significant had to do with the large sample size. Notice we had 1,200 for our sample size. So the moral of that is large sample sizes can lead to statistically significant results, while the difference between the statistic and parameter is not really enough to be considered practically significant. So a word of caution: beware of studies with large sample sizes that claim statistical significance, because the difference might not have any practical meaning. Okay, that finishes up 10.3. 10.4 is only putting it all together. So in 10.4, if you are still having trouble and need to see more examples, go ahead and go watch 10.4. And all it is, there's nothing new in there. It's just some extra examples to work through what we've done in in chapter 10 with these hypotheses tests. Okay, let me know if you need anything.